And this will take a minute, but it should go. And options. Oh, there we go, full screen. Okay, so let me turn myself. All right, I think we can get started. So in case some of the audience wondering who is this guy standing on the stage, maybe let me take 30 seconds to introduce myself before introducing our speaker today. My name is Shuo Sun. I am a GILA fellow, who joined last year during the pandemic, and that may be one of the reasons not every one of you are familiar with me right now, but I definitely looking forward to talking with every one of you later. So let's focus on our speaker today. Today's speaker is Jelena Vučković from Stanford University. Jelena is a Jason Huang Professor in Global Leadership in the School of Engineering at Stanford University. She is a professor of electrical engineering and by courtesy of applied physics. She is currently also holding the chair position of the Department of Electrical Engineering at Stanford University. She has many other affiliations at different institutes of Stanford. Most notably, she was the inaugural director of Q-Farm, which in my understanding is just our CU version, a Stanford version of the CUbit. It is a Stanford/SLAC Quantum Science and Engineering Initiative. Jelena received her PhD from Caltech in 2002, and then she spent 1 year at Stanford as a postdoc after she quickly joined the same department at Stanford as an assistant professor. Then she was promoted to associate professor in 2008, and finally as a full professor since 2013. She has received many awards and honors. I really have a long list here, but I'll just give a few most recent ones. So most recent notable ones, including the Mildred Dressel House Lectureship from MIT, James Gordon Memorial Speakership from the OSA, I guess it's Optical right now, the IET AF Harvey Engineering Research Prize, Distinguished Scholar of Max Planck Institute for Quantum Optics. The list really goes on and on. She is a fellow of APS, Optica, and ISSS. And Jelena also is a member of many science advisory board committee members, including MPQ, NSF Engineering Directorate, System X at Stanford, and also she serves as an advisor of several semiconductor technology companies. She is currently also associate editor of ACS Photonics, a member of editorial advisory board of NPJ Quantum Information, APL Photonics, and Nanophotonics. So all of these say that Jelena is really a prestigious researcher in this field, but what I can say is that Jelena is also a wonderful research advisor from my personal experience since I stayed 3 wonderful years at Stanford in her group as a postdoc researcher. So with that, I'll pass it on to Jelena, and Jelena, we look forward to your talk.
Thank you very much, Shuo, for your kind introduction. And it's really a great pleasure and honor to speak at this seminar. You may remember that I was supposed to visit you in person last year, but then pandemic happened and unfortunately we had to postpone. But it's really great to speak today and actually also be introduced by Shuo, who, as you heard, was my postdoc and who joined you over the past year. So I'll talk about our recent work on scalable semiconductor quantum systems, which is related to the topic of your initiative, and tell you about some of the recent progress that we made over the past year or two. And this really doesn't need an introduction for this particular community. You know that there is a lot of excitement regarding quantum technologies these days, and of course a lot of beautiful work happening at CU Boulder. We are in my group interested really in answering the question that is shown here. Can we really build scalable semiconductor quantum networks, sensors, simulators, and computers? And of course, you probably heard about announcements of these superconducting quantum processors from industry, and there is a lot of exciting work also going on in Boulder on superconducting systems, for example, in Conrad's group. Then you also know about atomic quantum simulators consisting of several hundreds or even thousands of atoms simulating quantum processes. And there is a long list of people working on this, of course, in Boulder. And I see on my screen that Cindy and June are here, but of course, many others. I'm here highlighting the work from Immanuel Bloch in Munich. But what we're really interested in is working on semiconductor versions of these systems, and the reasons are something that I'll explain a little bit later, but there is a potential to reduce significantly infrastructure because you don't really need to trap atoms. They're naturally trapped in the semiconductor environment, and you can get rid of a lot of the components and potentially scale systems up to even larger number of qubits. And naturally, these platforms that we work on have been considered for a long time for quantum networks and also quantum sensors, but we're also interested in whether they would potentially be interesting for quantum simulators and even quantum computers. And for implementation of all of these platforms, although some of the platforms are for the implementation for all of these technologies, you really need homogeneous long-lived qubits with good interfaces, and you need efficient connections between these qubits to build up large-scale entanglement. Often people are addressing particular pillars of quantum technologies with particular platforms, and some platforms are more suitable than others for certain applications. For example, superconducting systems are more suitable for quantum computing than for quantum networking. But in reality, if you have some platform that would enable long-lived qubits and they're optically interfaceable, and you can build up large-scale entanglement either on a chip or remotely, you could build all of these different technologies using the same platform. So that's what we're really trying to answer here. And for us, the choice of qubit are optically interfaced semiconductor spin qubits, really artificial atoms inside of optical structures in either diamond or silicon carbide. And Shuo, who joined you recently, also works on these particular types of impurities, core centers in diamond. You can view them, if you're not very familiar with what we're doing here, as naturally trapped atoms or ions inside of a semiconductor environment in either diamond or silicon carbide, but they also exist in other types of materials. So clearly you don't really need to trap them. You don't need MOT or some other mechanism for trapping them because they're already naturally trapped inside of the material, and then you can carve out whatever resonator or other optical structure you need around them. So you can view them as solid-state version of atomic cavity QED systems. Also, you can view them as kind of miniaturized version of circuit QED systems where you have a Josephson junction inside of a microwave cavity. But in our system, everything operates at optical frequencies. It's scaled down by a factor of about 1,000. We have to also use some sophisticated fabrication techniques to introduce these atoms or ions at desired positions and then carve out structures around. But the advantages, potentially relative to some of the other platforms, are that you work with semiconductors. For some of them, especially for silicon carbide, processing is very mature. There is a possibility of operation at higher temperatures of few Kelvin as opposed to millikelvin temperature operation for superconducting systems. There are already excellent optical interfaces, which is why these platforms have actually been used in state-of-the-art quantum network experiments, like the one in Delft in the group of Ronald Hanson and Stephanie Venner. And finally, the number of 2-qubit gate operations that you can perform per electron spin coherence time exceeds that of some of the other platforms, such as superconducting qubits. So in principle, you can also implement larger depth quantum circuits once you scale these systems up. So as I said, we're primarily working on color centers in diamond and in silicon carbide, and there are many different color centers that occur in these materials. In diamond, in particular, we're interested in group 4 impurities, which is at the moment silicon and tin vacancy color center. And if you look at the lattice of carbon atoms inside of diamond, these particular color centers are produced by removing 2 carbon atoms and adding an extra silicon or tin atom in between. And silicon vacancy color centers have been studied for a pretty long time, maybe about 10 years actively in the context of quantum information processing. And we made some interesting contributions there, and of course, many other groups. But the state of the art is that excellent quantum photonic interfaces exist for these color centers, and interaction between 2 qubits and a resonator in the same resonator has been demonstrated by the group of Misha Lukin and collaborators at Harvard. More recently, we started looking into tin vacancy color centers, which is exactly the same geometry of a color center as silicon vacancy. You have 2 missing carbon atoms and an extra tin atom inserted here. They have transition 0409 at somewhat shorter wavelength than silicon vacancy. But also they're inversion symmetric and to first order immune to electric field, which means that they're more stable to DC electric fields. And what is also important is that as a result of a larger ground state splitting, they can operate at somewhat higher temperatures than silicon vacancies. So you can actually obtain the same experiments and achieve the same results as silicon vacancies, but maybe at few Kelvin temperature as opposed to milling Kelvin temperature, which is still required for silicon vacancies because of the very small ground state splitting. And also they have a larger internal quantum efficiency, which is also important because without engineering sophisticated structure around the color center, there is a higher quantum efficiency, higher conversion to photons at the output, which is always important. And here, the state of the art is really that we, a few months ago, demonstrated a quantum photonic interface for this color center in a cavity, as I'll tell you a little bit later. And also in collaboration between Cambridge University in the UK, Mette Tature's group and Dirk Ringwood's group at MIT. They also demonstrated optical control of the spin qubit inside of diamond structure. So it's kind of catching up with silicon vacancies, although we're not there yet, but there are a lot of potential advantages, which is why people are switching to this color center. And the other material of choice is silicon carbide. And silicon carbide is very exciting for a variety of reasons. It's a few orders of magnitude cheaper than diamond, and that's why people use it to make fake diamonds. You can get it on 6-inch wafers from companies. Also, it's being used for MEMS devices, power electronics, heating elements, even abrasives. So it's really a material that is very available, and you can get it in high purity relatively inexpensively. But it also hosts a variety of interesting color centers that people have worked on. And I will not really go into details of all of these different color centers that we summarize here in the table. Just mentioned that my group primarily focuses on silicon vacancy in 4H polytype of silicon carbide, just a missing silicon atom inside of this particular polytype. But there are many other polytypes and other color centers and many groups working on them, and a lot of pioneering contributions on silicon carbide color centers have been made by the group of David Avshalom at the University of Chicago. So there are these very interesting color centers, which are kind of like naturally trapped atoms or ions inside of the solid. But then you may wonder why these platforms have not been scaled to the same scales as atomic physics platforms or ion-based quantum computing platforms. And the problem is really in inhomogeneities in this particular type of platform. And just to remind you, we work really with these individual impurities inside of a semiconductor. which we have to introduce by some method.
I'm watching a Zoom. I can't do anything about Chris.
Maybe we can just mute if it's not a problem. Sorry. We actually have to introduce them at the particular places inside of the structure, and that potentially introduces defects that affect properties of the qubit, right? The defects and dislocations inside of the surrounding semiconductor. And those inhomogeneities could be spatial or spectral, as I show here. Spatial inhomogeneities basically mean that it's very difficult to introduce them at desired positions and align them relative to optical structures, or introduce them inside of a regular array, as you can do in optical lattices. And then the spectral inhomogeneities are basically discrepancies between transitions of different atoms, which are a result of the changes in the environment. And again, in solid state, it's not vacuum. It's impossible to really perfectly control environment. We try to make it as close to perfect lattice as possible, but that's never really the case. And then there's discrepancies between different transitions that we have to address. And at best, we've seen 30 gigahertz spectral broadening, for example, for silicon vacancies. And in fact, I think Shallo was a co-author of this paper also when he was in my team, but we're trying to overcome that and reduce it further and overcome this spectral broadening in our experiments. So these spectral and spatial inhomogeneities are actually the main reason, in my view, why these structures haven't been scaled to the same scales as some of the other platforms. But I hope to convince you today that we have a set of techniques and also other teams that would enable us over the next few years to scale these systems to some potentially interesting scales for not just quantum networking, but also potentially quantum simulation. And for addressing spatial inhomogeneities, we've developed in collaboration with the groups of Ziak Shen and Imke Losh at Stanford, the technique of shallow ion implantation and subsequent overgrowth. Really, the idea here is to introduce color centers at desired positions inside of the structure with minimal damage. And normally people introduce color centers by high energy implantation, which of course always introduces damage and moves some carbon atoms around and changes the local environment for color centers. What we instead did in this work was shallow ion implantation at much lower energies. And by doing that, we can actually use a lithographic mask for the chip itself, then do implantation at lower energies, which ends up with these impurities close to the top interface. And then we finish up with growth of high purity diamond so that color centers are not right next to the surface. And with this technique, we actually can introduce color centers at any position in the diamond structure where we like. I mean, even in the shape of my group's logo, which is not useful for science, but it just shows that we have a control over this. And then subsequently, we can align optical structures to whatever positions of color centers we have. So that's one technique that could be used to address spatial inhomogeneities. But then for spectral inhomogeneities, we developed a few different techniques that could be used to overcome these residual spectral inhomogeneities. And at the moment, most recently, actually, we focused on stark shifting in both silicon carbide and diamond. In silicon carbide, we can just use DC stark shift to tune the color center transition across the whole spectrum of inhomogeneous broadening. So you basically just put electrodes and tune the transition wherever you like. And in the process, you don't really degrade stability and properties of the color center. And then we also did the same for diamond, but of course for diamond color centers that I presented, there is no first order stark shift, only quadratic one, because they're inversion symmetric, which is why you need larger voltages, but you can still use this applied voltage to compensate some residual inhomogeneity in spectrum. And also we looked into other methods. For example, Shallo developed a method of resonant Raman scattering, optical driving, where you could in principle control different color centers, not with electrodes, but also with different lasers, detuned lasers. So we have a set of these techniques that we can use for controlling spectral and spatial inhomogeneities. We also recently looked into using these electrodes and applied microwave fields for Fourier engineering, kind of going beyond just simple Stark shift, in this case for color centers in silicon carbide, but instead engineer microwave drive on the color center in order to engineer the spectrum. And this is a drive that contains a few different harmonics, but we've also shown that we can optimize that drive and completely change the spectrum at the output. And these are experimental results for a single color center, but the idea here with Fourier engineering is that potentially you don't really need separate electrodes for each color center in the structure, but maybe you can optimize the drive on a single electrode and drive multiple color centers and make them talk to each other. So that's the direction in which we're going. So I showed you some exciting kind of long-lived qubits that exist in this diamond and silicon carbide. I showed you also techniques how to overcome their inhomogeneities that have been a big bottleneck in building up scalable systems. But that's only one part of the story. In addition to these qubits, we also need to connect them and to build large-scale entanglement. And we need to build optical connections efficiently because we use photons to communicate between these qubits. And we also use photons to control state of the qubit, spin state of the qubit. And I'll now like to spend some time telling you about optical connections. So to build efficient optical connections, of course, we rely on photonics because the idea that we're pursuing is to do everything on chip scale. But it turns out that traditional photonics doesn't have a lot of functions that we need in order to build these systems. And also often efficiencies are not sufficiently large. Even in commercial classical photonic systems, people often use elements that have efficiency of around 50%. And that's okay if you are working with classical system, but of course it's not really okay for quantum systems, which is why we've been pursuing this idea of optimized photonics or inverse designing photonics. And this is something that my group has been working on for about 15 years or so. And it's a field that is rapidly expanding and more people in photonics community are accepting it. But really the idea is to combine optimization techniques with fast electromagnetic solvers and search the whole parameter space of whatever can be made in a certain material for a given function that you would like to address. And as a result of this, since you're searching the whole parameter space, you often end up with designing devices that don't look at all like traditional photonic structures, but they beat state of the art in terms of footprint, efficiency, and also robustness to the environment, errors in fabrication, which is of course all very important, in particular if you're scaling the system up, because you don't really need a lot of knobs to tune every single element in the circuit, and efficiencies are much higher. And we initially in this process worked on kind of simple devices like wavelength splitters. These are all actual demonstrated structures. So this was a wavelength splitter. There is another one behind me. But then we also, over the past 5 years, moved to new functionalities like on-chip particle accelerator, which is ultimately new application of photonics, high energy physics. And also we work with commercial foundries on translating the whole process to large scale integration. And these structures here that you see on the screen are silicon. I'll also show you later that the process is material agnostic, and we work with a variety of other materials, including diamond and silicon carbide. But also, if you're interested in playing with this inverse design approach, we have an open source version of our software, which we call SPINS, Stanford Photonics Inverse Design Software. A basic version called SPINS-B is on GitHub on my group's webpage, and you can download it and play with it. And also there is a full version which people can license from Stanford, and also many groups are using it for their work. So let me use this kind of ultimate application, new functionality for photonics, which is particle accelerator on chip, to explain what we're doing here before going back and telling you about quantum optics. When we mention particle accelerator, of course, you always think about these gigantic structures. On the left, you see Stanford Linear Accelerator, which is a couple of miles long next to Stanford, or CERN, Fermilab. These are gigantic facilities that are miles in size and exist only at limited number of places around the world where people have to go and do their experiments. Of course, there is a whole range of energies for accelerators. High energy physics is the range of these highest energies, giga-electron volt and above. There are a lot of accelerators in the mega electron volt range, which are used in radiation therapy, in medicine, and also in imaging, scanning. And they still occupy the whole room and are pretty expensive, which is why they don't exist in every hospital around the corner. For cancer radiation therapy, people have to go to some specialized facilities and usually some more established hospitals or facilities. So there is this bottleneck in size and cost and location for accelerators. And that's something that we've been trying to address with our collaborators. And my colleague Bob Bayer at Stanford for a couple of decades have had this idea of using optical wavelengths instead of typically used microwave and radio frequency waves to accelerate particles. So in traditional accelerators, you use either radio waves or microwaves to accelerate charged particles. But what if you use different part of the spectrum with much shorter wavelength, right? If you use infrared light. And in principle, you should be able to scale down the size of accelerator by a factor of about 10,000 relative to state of the art. But you can't really just take everything and scale it down by 10,000. You have to redesign everything so that it works for optical waves. And that's not a trivial process. We don't really have those functionalities in photonics. Nobody really has any idea how to make stage of a laser-driven particle accelerator, which is why we rely on inverse design. And here you see a movie of how we search that whole parameter space to design a stage of particle accelerator. And what we define as the target function is acceleration, maximum acceleration for an electron, which arrives into this structure through vacuum with particular initial energy, 83 kilo electron volts in this case, which was our experimental case. And we want to make sure that for the couple optical field to this dielectric structure, we always provide the kick for this electron in the right direction. We always accelerate it. And you see here how software really searches through the whole parameter space efficiently using multidimensional gradient descent technique and changes the structure. And you see how the field changes at the bottom in such a way that acceleration is maximized. And once we design this, we can make it. Here you see the final structure made in silicon on the left, and on the right, you see how field changes, and it's highly non-intuitive. Nobody would really design these features by hand to look exactly like this. But then again, for an electron that would propagate through this structure through vacuum with that given initial energy, it would be accelerated. And we did experiments for this, for a single stage of accelerator, which is 30 micrometers long. Here is how it looks like. It's made in silicon. Again, the patterns that I showed you before. It also has these inverse design couplers because we also have to couple light from very powerful lasers, which are very short and energetic broadband pulses. So there are also couplers that don't really exist already readily in photonics that we had to optimize here. And we did the experiment where we couple electrons to this vacuum channel with initial energy of 83.4 kilo electron volts, and we look at what happens at the output when we turn the laser on or off. And we were able to demonstrate 30 mega electron volts per meter acceleration gradient, which is already on par with some already useful accelerators. So let me show you the experiment. Again, repeating just the structures that I showed you. When the laser is off, then electrons enter and exit the structure with the same energy. That's the blue curve, but then when laser is on, you see electrons getting accelerated by about 1 kilo electron volt within this 30 micrometer length, which is converted to 30 mega electron volts per meter acceleration. And keep in mind that this is just a single stage of accelerator. Like in traditional accelerator, you need hundreds or thousands of stages to really achieve the target energy, which tells you that within an inch or a couple of inches of a silicon chip, we can really go from 80 kilo electron volts, which means the initial energy of electrons we have here, to about mega electron volt range for the existing structure, which is already very interesting and exciting for radiation therapy or some material science or imaging applications. And that's what we're trying to do now, integrating hundreds or thousands of these elements on the same single chip. And we don't want to do that by hand in nanofabrication facility, but instead we're working with commercial foundries on building this on-chip accelerator. So that was kind of the explanation of what we're doing. Now I'd like to just show a couple of state-of-the-art examples and then go back to quantum optics. So as kind of state-of-the-art example, I'd like to highlight something that we recently did in collaboration with several groups that are all part of our DARPA PIPES team, including the group of Scott Papp from NIST and CU Boulder. And this, again, is a classical photonic application, but enabled by inverse design. And it's the application where we're developing optical interconnects for computers, for classical computers. As you probably know, in data centers, people use photonics to connect the different servers to reduce energy consumption and increase operating speed. But there is a push to really bring this optics to connections between different chips or even on-chip connections inside of the computer for the same reason. And that's this large program that we are part of is working on. And the platform that we are developing is based on this multi-frequency source, which is actually frequency comb developed by Scott Papp's team. Then we use what is called wavelength division multiplexing. That's a traditional approach for encoding information in optical communications, where we use different wavelengths as different channels for communication. But then we also use another dimension here. Instead of just using different wavelengths, we also use different spatial modes. And by that, we multiplicatively increase the number of channels that we can communicate. So for example, for 4 spatial modes and 52 wavelength channels, you can actually communicate 4 times 52 channels overall. And that is very useful for both on-chip and chip-to-chip communication. And of course, we're not the first ones who thought about using spatial modes for communication. You know, people use that for fiber optic communication and have thought about it for on-chip communication. But there have been a lot of bottlenecks in terms of building components for this, but we designed them with inverse design. And what is shown here is a component where you can convert different single mode inputs, single mode waveguide inputs to different spatial modes at the output in a very small footprint of 6 by 6 micrometers. So that's what we call mode division multiplexer or demultiplexer. And these are experimental results of this structure. They're extremely broadband so that they can accept all the different channels from the frequency comb, and they have excellent properties as theoretically predicted. And, you know, I just like to kind of point out that these structures all look alike very much, like the one shown here and the one behind me, but they have very different functions. They're very different operation, and they're really, these patterns are designed by this sophisticated algorithm. And once you build everything, and you know, this whole circuit is even built inside of the semiconductor foundry, and you try to communicate using this platform that I just described, we're able to approach terabit per second communication rates with very small bit error rate of 10 to minus 12, which is already very useful for communication, even in practical environment inside of a computer or in data centers. So now, you know, going back to quantum optics, how does that fit the idea of quantum optics, right? Of course, there are a lot of classical photonic components even in quantum circuits, but we would like to also implement new functionalities and increase the efficiency of a lot of components and build some new elements and put everything together so that we can build large-scale entanglement. But to remind you, our materials of choice are diamond and silicon carbide, and these are really not traditional photonic materials. Most of the photonics that you would find you know, in papers today or in commercial circuits would be based on silicon. Silicon on insulator, and silicon on insulator is a platform that was commercialized about 20 years ago, and that's exactly when silicon photonics kicked off. Bulk silicon was commercialized 40 years earlier, and that's of course what propelled also in semiconductor industry. But for photonics, we always need some kind of guiding layer, you know, silicon on insulator or some high index layer on insulator or some method of making this guiding layer and making the photonic circuit. And then for the past 10 years, there has been also a lot of excitement around lithium niobate photonics, because thin film lithium niobate was commercialized around 10 years ago, and that was about 20 years after commercializing bulk lithium niobate. And lithium niobate is a very exciting nonlinear optical material, and there is a lot of nice work also at NIST on this particular platform, and in Boulder, also by Scott Diddams and Scott Papp. But again, part of the reason why this platform has become even more interesting is because there are these thin films that are commercially available, and people can get the wafer and design structures and fabricate devices. But for diamond and silicon carbide that we're talking about here for quantum optics, we don't really have thin film on insulator that you can get commercially. You can get 6-inch wafers of silicon carbide, or you can get a few millimeter chips of bulk diamond, but then you have to figure out how to make photonics. And that's not a trivial process. And I'll now like to show you how we're making photonics in these materials with very high quality for both diamond and for silicon carbide. Here you see some actually fabricated structures, and you also see some non-intuitive inverse designed elements that we're able to fabricate here. And all of these also incorporate color centers that I was talking about at the beginning. So for diamond, you can't get really thin film diamond on an insulator commercially. You have to make it yourself, or you have to do some kind of bulk carving to make photonics, and that's what we do. It's a method that was pioneered by Paul Barkley at the University of Calgary, and then it was adopted by us and others. And it's really essentially carving. You start from bulk block of diamond, and then you lithographically define whatever you would like to fabricate, and then you etch down, and then you etch sideways, and then you end up with these suspended structures that I think really look beautiful, thinking that this is a block of diamond. But of course, diamond is not an easy material to process, and fabrication is not really trivial, but we're able to make very high quality structures in the process. And I'll show you some of the exciting experiments later on. And these are also this is also compatible with the inverse design that I was talking about. So here you see some non-intuitive elements that are splitting light and combining emission from two different resonators. And we can do all of this fabrication without affecting properties of the color center, like thin vacancy in diamond. Recently, we managed to do that and demonstrate quantum photonic interface for thin vacancy in diamond, which means that we had a structure with thin vacancy color center. We fabricated resonator. These are also inverse design couplers. And we were able to show enhanced emission from this color center into a particular cavity mode. And very soon after this demonstration, also Harvard group of Mark Launcher demonstrated likewise quantum photonic interface for the same color center. So you see here how quality of this structure looks like. I mean, this was not a trivial development relative to silicon vacancy color center, because we have to operate at much shorter wavelength. 620 nanometers as opposed to 740 nanometers. All of the photonics has to be smaller, and all the features have to be smaller, which is why it took us a while, both for us and for Harvard, to develop this new interface. So here is a cavity with a good quality factor. Then here we look at what happens as we scan the cavity resonance relative to the transitions from this thin vacancy color center. When they are on resonance, we see large enhancement in the emission from 0.409. And then if we measure, we do time result measurements and measure emission from this single color center, as confirmed by photon statistics measurements, we see large suppression in radiative lifetime, and we extract the spontaneous emission rate enhancement of about 25. And you see here also, as expected, Lorentzian line shape in the spontaneous emission rate as you're scanning this color center transition across the cavity resonance. It's not strongly coupled yet, but we're working towards that, and we hope to be in the large cooperativity regime soon. And then likewise for silicon carbide, we have to make up photonics, right? You can get these bulk wafers even on 6-inch scale, but you need to go from something like this or this bulk wafer to really sophisticated chip that has photonic components. So how do you make this guiding layer, right? You have to somehow produce your self-guiding layer because there is no thin film silicon carbide on insulator that is commercially available. And we tried a variety of things, but what worked the best for not affecting properties of the material and color center itself was bonding of silicon carbide wafer onto oxidized substrate, silicon substrate, and then grinding and polishing until you get rid of most of silicon carbide. And then you have a thin film of silicon carbide sitting on insulator, typically few by few millimeter dimensions, but it's large enough to make a lot of photonics. And this method is also scalable to wafer scales, although that's not something that my graduate students would be doing at Stanford, probably in industry. So with this approach, we're actually able to make very high quality photonics. At the moment, we have quality factors of resonators in the near infrared exceeding 5 million and loss of 0.08 dB per centimeter, right? So this is comparable to lowest loss photonics. It's actually lower loss than silicon photonics. It's almost as good as silicon nitride photonics made at EPFL and IBM, which has a record low loss. We're also able to make inverse design structures, resonators. And these are also suspended structures, or you can leave them sitting on this oxide layer, which is a lower index layer. And that way you can actually have high quality structures. So there are more of the pictures of resonators shown here. You can do all of that without sacrificing properties of color center. Again, silicon vacancy, transition, tuning relative to cavity resonance, or actually in this case, tuning cavity resonance relative to different transitions. And we can enhance on resonance by a very large factor. So properties of the color center have not been sacrificed in the process. And I'd like to show you some really fresh results out of the lab that even bring this on par with diamond color centers. I mentioned earlier on that state-of-the-art for silicon vacancy in diamond is the coherent interaction of two silicon vacancies inside of the same diamond nanocavity, which was demonstrated by the group of Misha Lukin and Marko Lončar and collaborators at Harvard. Very recently, we have shown the same coherent interaction between two silicon vacancy color centers in silicon carbide resonators. And here we relied on silicon vacancy and material orientation, which leads to this dipole orientation in the vertical direction. That's why these dipoles are shown as vertically oriented. And that's also the reason why we relied on the microdisc resonators, so that we could work with the TM modes that couple well to these TM-oriented transitions. So here you see two different color centers, two different emitters that are positioned inside of the microdisc resonator and the cavity resonance. We have a really nice Q factor, and we have also very narrow emitter line width, despite this whole process that we go through of grinding and polishing and subsequent resonator fabrication. And around resonator, we also have the waveguide that is coupled outside of the cryostat. So there are two color centers within a cavity resonance. We can measure transmission through the cavity, see dipole-induced transparency. We're kind of not in the large cooperativity regime, but we're approaching cooperativity of 1. So we're starting to see transitions also in transmission induced by these color centers. We also see significant reduction in lifetime and good Purcell enhancement for both of these color centers independently. And then for coherent interaction, we do see that in the case when they're both coupled to resonance, we do see coherent collective interaction and super radiance from statistics measurements for the system. So as expected, we can actually observe this bunching in the photon correlation measurements, which is actually a signature of super radiant behavior and collective coherent interaction of two color centers with the cavity mode. What you see on the left is, as we're changing the tuning between these two color centers and the cavity resonance, these dips in transmission, as known as dipole-induced transparencies, are kind of changing positions. And then when they're on resonance with each other, you see a single dip in transmission. So we are not in a large cooperativity regime, but we're starting to see signatures of the collective interaction and super radiance. These are extractive cooperativities for the two emitters. And this is not an optimal configuration to do these experiments, because we work with TM TEM-oriented emitters and not the best cavity design. We work with microdiscs that have larger volume, but we're now, from collaborators, we received the right orientation of the material where the same color centers would have TE, in-plane dipole orientation, so that we can embed them in much smaller volume photonic crystal cavities and observe larger cooperativity and even stronger interaction. So anyway, I wanted to share these results with you, which are again fresh results out of the lab, just highlighting that in terms of state of the art on the level of interaction or level of scaling that people have seen, silicon carbide color centers are pretty much at a similar stage as color centers in diamond, where the collective coherent interaction of two color centers and the same nanoresonator has been observed. And this is very important because as those of you working on atomic physics or other quantum platforms know, we do need this platform. If you manage to couple a larger number of atoms to the same resonator, could be also used for quantum simulation or for generation of some interesting quantum states of light. So in silicon carbide, apart from the coupling of color centers, we've also investigated nonlinear optics effects. Silicon carbide is a very interesting material. And actually, there is no other material that has at the same time all of these interesting properties that, as opposed to silicon carbide, right? So you can build electronics directly on this material. You can build MEMS. People use it for heating elements, but you can also make high quality photonics, as I showed. There are high quality color centers comparable to diamond. And also silicon carbide has a very respectable second order optical nonlinearity, Chi2, and third order nonlinearity, but second order nonlinearity is about a factor of 3 lower than for lithium niobate. It is a factor of 3 lower, but on the other hand, fabrication of structures is way easier than lithium niobate, and photonics is of much higher quality. And that can compensate for this initial degradation in the second order nonlinearity, because we already have very high quality photonics. And once you have a thin film of silicon carbide on insulator, fabrication of photonics is exactly the same as fabrication in silicon. So you can, in principle, do it in a commercial foundry. They agree it's a fully CMOS compatible process, and you just in your fabrication facility at the university can use exactly the same tools that you would use to fabricate silicon. So it's super simple. The key step is thin film fabrication. Recently, inspired by this nonlinearity, we also investigated nonlinear optical effects, and we're actually continuing to work in this direction, also in collaboration with Scott Papp's team and collaborators at NIST and elsewhere. And this is very exciting for us because by fabricating these new structures, high quality structures, we've been able to observe single soliton, build microcombs with comparable thresholds to those in other materials, including silicon nitride and tantala that NIST is pursuing. We've also observed soliton crystals, kind of excitation of particular lines in these soliton combs. And we've also recently looked into subthreshold behavior, both of single soliton and soliton crystal, by building this single photon optical spectrum analyzer. And we looked below the classical optical spectrum analyzer noise floor by this instrument. And we were very excited to see in the soliton crystal these additional lines that occur as a result of the frequency mixing of the soliton crystal lines. And this is interesting because it's really looking deeper using a tool and techniques that we have from quantum optics into the behavior of soliton combs. But potentially it also has some applications in quantum optics, because in some special regimes of operation, you can observe a massive entanglement between the spectral lines in these soliton combs. We're not really there yet because we have to redesign the structure in order to preserve the entanglement at the output. But we have seen that in the regime where we are experimentally, we have the correlations, the right type of correlations between these soliton crystal lines. And this experimental demonstration of the correlations between different lines in the comb that we measured are shown on the bottom right. It agrees with the theory. Again, these are expected correlations and is still in the classical regime, but we are expecting once we redesign the structure to also observe multimode entanglement. And there are some interesting proposals out there for use of this entanglement in frequency combs for quantum simulation. So with that, I'd like to kind of wrap up my talk and say a few words just to summarize everything that I've been talking about. First, common theme on the photonics side is that I really believe that photonic optimization is crucial for implementation of both classical and quantum photonic systems. We've been working on it actively. This can be applied to any material. It's material agnostic, works in silicon, works in commercial foundries. You can build new functionalities, but also works in new materials for quantum optics and enables new functions both in diamond and in silicon carbide. And you can also build structures that are much higher efficiency or have the right type of functionality, or you can do it in such a way that you can also embed color centers inside of them. And if you're interested in playing with these optimization tools, you can start with our open source version on GitHub, the SpinsB. So we use actively optimization in photonic design. And of course, this could also enable improvement in other types of platforms, including atomic physics platforms, where you also need photonics for control and for light matter interaction. Also, I really believe that diamond and silicon carbide are promising platforms for quantum technologies, and possibly even beyond their natural application in quantum networking or quantum sensing, also in quantum simulation and maybe quantum computing. And with that, I'd like to thank my group and our funding, and thank you all for your attention. Thank you.
All right. Any questions? Yes. This is Anna Maria.
Hi, Anna Maria. Sorry, I don't hear you, so Shuo will have to
I think
repeat the question.
Do you hear this one okay?
No, I hear you, Shuo, only.
Oh, I see. That's why I hand this to you, but maybe this.
I'm sorry, can you hear this now?
Yes.
Okay, there we go. Sorry about that.
Thank you. Thank you. Can you hear me now? Yes.
Yes, yes.
Okay.
Hi. Hi, Anna Maria.
Hello, Jelena. Nice, very nice talk.
Thank you so much.
So I have a question. When you couple the two impurities, what is the dependence of the coupling on the separation? I mean, the cavity, I imagine, is not uniform. So is there any dependence of the coupling with the position of the particles, or you are matching coupling?
Oh, absolutely. I mean, it's an excellent question, and there is a large dependence. And in this particular experiment, we don't know the exact position of the color centers. They're somewhere inside of the cavity. So we played also, I didn't show those experiments, with exciting different standing wave patterns inside of the structure. And with that, we can also change the coupling between any changing kind of the modes that were exciting. And with that, we can also change the coupling because, of course, there is a spatial dependence. But we don't know the precise position, right? So the coupling that you see here is degraded because, not just because of the larger volume of the microdisc resonator, but also because of the spatial misalignment. We do have techniques that I was showing for controlling spatial positioning, but that was not really done in this particular material in silicon carbide. We're looking into doing it going forward. And we are also, as I mentioned, trying to actually work with different crystalline orientation and different type of cavity cavities where the interaction would be stronger. So we don't really plan to spend too much time aligning resonators to microdisks, because I think photonic crystal resonators are much better. Does that answer the question?
If there's any more questions, please feel free to raise your hand. I'll run the mic over to you. If you're on
I
Zoom,
see, yeah.
I think you can just unmute yourself and speak, and that should be fine.
Yes, I see June has a question on Zoom. He raised hand. Hi, June.
Hi, Jelena. Can I ask the question?
Yes, of course, please.
Well, thank you very much for giving this wonderful talk.
Thank you.
If possible, I have one short question, maybe one relatively longer question. But the short question is, when you talk about electron acceleration on the chip,
yes,
you mentioned that right now you have a single chip, a single stage. But I guess a single stage could mean both longitudinal for energy boost and as well as in sort of in parallel to boost the current. Eventually, you want to apply with large brightness.
Yeah.
Is it possible you could do this with a large input of several stages of acceleration running in parallel?
Yes, in principle, it is possible. We're not really, in this case, the stage that I showed as design just has a kind of single current input, and it's coming from the converted electron beam microscope. That's why energy is 83 kilo electron volts. Okay. And also the beam itself is larger than the vacuum channel, which is why a lot of electrons were not really coupled to the structure itself. I mean, we plan to really have a tip on the chip itself so that the dimensions of the tip are matched to the dimension of the waveguide. And then, of course, longitudinally, there would be a lot of stages that would be cascaded on the same chip. So it wouldn't be multiple chips, but a lot of stages that are cascaded next to each other on the same chip. And since one stage is, let's say, around 30 micrometers, you can have hundreds of stages in about an inch, right? Few centimeters. And that would bring you to around mega electron volt. But then for boosting current, in principle, you can do it in parallel, as you were saying, with a set of different electrodes and tips and multiple stages that are placed next to each other. And, people are, we're just part of a very large collaboration. Different people in the team work on electron tips and bunchers and also laser sources for this. A lot of people from Germany who Peter Hommelhoff works on tips, and Franz Kartner on laser system and so on. I really work on photonics here. But people are really also working, thinking about doing kind of in parallel multiple of these accelerators, because of course for radiation therapy and a lot of applications, even in mega electron volt range, you need the larger currents, as you pointed out, because the current from this single structure would not be really sufficient for a lot of applications. Maybe for some imaging is fine. If you're making kind of a small free electron laser or some X-ray source on chip, if you just want to do imaging, it would be fine, but not for therapy. And there are people actively working on this, on developing laser systems for this, and also developing sources and bunchers, but we're not there yet. We're just characterizing single stage and kind of coupling of a few longitudinally cascaded stages.
Really nice. Actually, if we still have time, I just have a question about the noise. That at the very end, you were talking about quantum correlation of the modes.
Yes.
In a single soliton.
Yes.
Could we go there? I was actually not clear about your classical OSA noise. Is that what is that classical noise? Is that the optical spectrum analyzer noise? That's technical noise. But are you talking about actual shot noise of your comb system, and you're starting to dip below the shot noise? I wasn't so clear. No,
this is just a technical kind of noise of the OSA, the detection level that you can measure inside of your OSA, right? And we basically just use, we build kind of homemade spectrometer combined with single photon counters, and we can essentially detect single photons in this experiment and perform correlation measurements.
Okay, so the single photon detector, of course, is not limited by the OSA. So you're essentially doing some heterodyne technique, right?
Yeah.
You're against another source, and then
yes.
you're measuring and you're starting to see sort of a quantum correlation between the different distinct modes?
We see theoretically predicted correlations, as you see here, which is, you see this, we can call it quantum correlations because it's a super Poissonian behavior, but that's expected because these are parametric processes and cascades, because these lines here are produced by mixing lines of the soliton crystal, right? And you do expect bunching and super Poissonian statistics. So we can call it quantum correlations. I mean, it's a super Poissonian. I mean, it's not really classical light, but it is not quantum entanglement. We don't expect to see quantum entanglement here, just bunching between individual lines. Yes.
Yeah. Thank you.
Yes. Thank you.
Hi, Jelena. This is Adam Kaufman.
Hi, Adam.
I had a somewhat basic question about the accelerators. So should I understand this that basically you have this pulse that comes in and it just drags the electron through a Ponder mode of interaction? Like what is the actual acceleration mechanism physically?
Yes. So this is actually kind of a resonant cavity-based accelerator. And people use those kind of cavity-based accelerators also in microwave and radio frequency wave accelerators. So if we just go back some number of slides, I can show you a picture. Maybe it's just easier to go back to that and show it to you, because it would be equivalent of this microwave, coupled microwave resonator type of accelerators. So here we go. Probably. I think this one would be probably the best to show here, right? So if you look at what's going on, or maybe on the next one here, this one with the whole movie. If you look at what's going on here is we couple light sideways, right? And this, you propagate electron through this structure, but these optimized structures on the left and right in some way act as mirrors, right? So you build some resonance in the horizontal direction, as you see here, and then your electron propagates here, but in that resonance, spatial field pattern is such that it's matched to the initial energy of the electron, and with that initial energy, you are accelerating it in the right direction, right? But what is happening here is you don't really have field propagation in the direction of electron propagation. Field is resonating essentially in the direction orthogonal to the propagation of the electron. Does that make sense?
I think so, yeah. So it's not actually a Ponder mode of interaction. Like these are all effects that are occurring close to the actual optical frequency, or no?
Well, this is happening at 2 micrometer wavelength. I'm not sure if I heard your question, but we couple light at 2 micrometer wavelength from the pulsed laser. And this is coupled on a side. I mean, you can kind of see it on the through this coupler. It propagates down the slab waveguide and gets to this structure here. And then inside of this structure, it builds up the field kind of low Q resonance with a particular field pattern that is shown here. Resonance would be between the left and right mirrors. So that's kind of 90-degree rotated picture of this. But your electron would be propagating through this channel, right, between the 2 mirrors. So the spatial field pattern is matched to the energy of the electron and velocity.
Okay, thanks.
Hello.
Yes, please.
This picture, this particle accelerator, it's the most fantastic science fiction alien geometry. It's wonderful.
Thank you so much.
Can you explain why it is that it is asymmetric? Maybe this is an easy question in electrodynamics, I don't know. Or is it just that the gradient descent does not respect the symmetry arbitrarily, and it's just the 2 sides of the channel are degenerate in some sense?
I mean, this is an excellent question. For this particular function, it doesn't really have to be necessarily symmetric along the axis, because all that we constrained in the optimization is the particular field flow profile along the axis where the electron propagates, right? So you can actually achieve that even with the structure that is asymmetric in the direction orthogonal to the direction of propagation. But the structure is periodic, of course, for that particular stage, because within each stage, electron propagates with the same energy and velocity. I mean, as it gains energy, you adjust stages eventually. And you can see for some functions like the one behind me, which is a valence splitter, structure is also not symmetric. There is no reason to be symmetric because you're splitting 3 wavelengths. But in some cases, it has to be symmetric. I mean, you are expecting it to be symmetric. For example, if you're working on, and I showed some examples in Diamond, like you're working on wavelength splitter from 2 exactly the same resonators. What is interesting is that even if you don't enforce symmetry, symmetry would naturally appear in the process of design. And I can go there and show you that picture a little bit later. I think it was shown, but here is an example of the naturally occurring symmetric structure. So there, because of the symmetry of the problem, the structure has to be symmetric. Does that answer your question?
Yes.
Sorry, my 6-year-old daughter just started her piano lesson, so you may hear some piano in the background. She's pretty loud.
Yeah, I think we are close to end as well. Any other last-minute questions? All right, so if not, let's thank Jelena again for the wonderful talk.
Thank you so much.
Thank you very much, Jelena.
Thank you. Thank you, and hope to see you in person soon, here or in Boulder. Thank you.
Thank you.
Thank you.